Hi guys, what I want to talk to you today about is standard solutions. What a standard solution is, it's a solution of a really accurately known concentration, and we often use these for analysis. So I'll give you just a really quick example of this. I'm not going to go into it too much, but say we have a 0.00, actually no, let's say we've got a 0.1001 mole per liter solution of hydrochloric acid. And we have a sodium hydroxide solution of unknown concentration. I know that these react in a 1-to-1 ratio, okay, to give me sodium chloride plus water. Let's be good and put some states in. Okay, I know that at the end of the day, these are going to neutralize each other, an acid and a base. Okay, they're going to neutralize each other to give me a neutral salt, which has a pH of 7. Okay, which I can use an indicator to find when it's reached this point. So I know when they've reacted in a 1-to-1 ratio. If I know the volume of this that I used, and I know the volume of this that I used, okay, so let's just say, for instance, that I used, I don't know, 25.00 mils of this, and I used, I don't know, let's say 28.00 mils of this. Actually, yeah, let's just say 28.00 mils of this. I can actually work out that, well, the number of moles of this is the same as the number of moles of this. So I can calculate using C and V the number of moles of this using N equals CV. Okay, and then I can flip that back and I can say that C equals N on V. Okay, using that same N that I worked out from the first part, and I can calculate this concentration. That's what it's useful for. We're going to do that in year 12. But what I want to talk about now is actually preparing these accurately known, these solutions of accurately known concentration. And you can't use anything to produce them to start with. So if I actually tried to use hydrochloric acid, or I tried to use sodium hydroxide to start with to make these solutions, I'd be in a little bit of trouble, and here's why. Here's the properties of a primary standard. We have them here on the left. So they need to be solid to start with because it makes them easy to weigh. Remember, a scale, the scales in the lab are our most accurate piece of equipment. They're far more accurate than any volumetric glassware that we have. So if we want to know something really accurately, it's actually better to weigh them. So we prefer a solid. Now, this actually rules hydrochloric acid out straight away, because hydrochloric acid is actually gas at room temperature, and you'd actually have to bubble it through the water if you wanted to know exactly how much of it you had to prepare a solution of it. So that's straight out of the question. Now, sodium hydroxide is a solid, so that's good. Now, the next question is that, can we obtain it in high purity? And the answer is generally no. Even if you got it in a really pure form, it has a little problem in that it does this. It reacts with carbon dioxide, okay? It reacts with carbon dioxide and water. And so if you have a scale here, and you're trying to weigh some sodium hydroxide on that scale, and that scale reads 7.000. Let's say you've got a really accurate scales, okay, which we do have, okay. We're not at school, but you can get these. They're quite expensive. Here's that pile of sodium hydroxide. Now, is that whole thing sodium hydroxide? Do we have 7.000 grams of sodium hydroxide? Or has it absorbed a little bit of carbon dioxide? And do we have, I don't know, 6.000 grams of sodium hydroxide plus 1 gram of carbon dioxide? I don't know. So if I go and make a solution, with this now, I actually don't know how much sodium hydroxide I have in there. It's a little bit of a problem. So that's the issue with these two things. They both have a known composition and formula. Sodium hydroxide and hydrochloric acid, I mean, their molar mass is relatively high. I mean, 35.45 plus 1, so it's about 36. Sodium's 23 plus oxygen, which is 16, that's 39, so it's about 40. So, I mean, they're both relatively high, and they're not huge. You could probably do better. The reason they need to be high is you have a smaller percentage error when weighing. Remember that there's a little bit of uncertainty in your last significant figure when you're weighing things out. Now, we don't have the privilege of having 3 decimal places at school. our situation is like this. So our uncertainty is even greater. You can usually say, people say it's about plus or minus half of the last significant figure. So 0.005 is probably the uncertainty on our scales. That's reasonable. Now, what is that as a fraction of what you're weighing? That's going to be a little bit of an issue. So we know that we calculate the number of moles from mass on molar mass. Okay, so let's have a little look at this. If I have something with a relatively low molar mass, the problem is that my percentage error is going to be greater. Okay, if it's got a low molar mass. So consider this: if this situation is, if I have 1.00 grams, well, I know that this is plus or minus 0.005, right? I'm going to divide this by, let's say we used hydrochloric acid, right? So it's 35.05, so 35.45 plus 1.008. So it's going to be 36.458 grams per mole. Now, the uncertainty of this is quite small as well, but these multiply, so this has an uncertainty as well. When I divide this by this, this number as a fraction of this will tell me how uncertain my final figure is, which is a little bit of an issue. If I have something with a higher molar mass, say for example, let's use one of these, like oxalic acid, which is a really good primary standard, 126.07 grams per mole. Well, 0.005 as a fraction of that is far smaller. So when you're working out the number of moles, you end up with a far smaller percentage error. So that's the reason for that. Anyway, moving on. What makes a good primary standard? Let's start with oxalic acid and let's say why this is better than using hydrochloric acid to start with. Well, firstly, it's available as a solid, which hydrochloric acid isn't. We also we know its molecular formula very well. It's C2H2O4. Now, it's got two waters that come in every crystal, but it's very accurately known. They're called, we say that this is hydrated, okay, water of crystallization. So for every crystal, so every molecule of oxalic acid, it comes with two waters when it crystallizes. As long as we know that, we can go ahead and calculate it. So if we calculate the molar mass for this, it's 1, 2, 3, 4 oxygens plus these two, so 6 oxygens, right? 1, 2, 3, 4, 5, 6 hydrogens and 1, 2 carbons, which are implied in this skeletal formula. We know how to calculate that really well. Where we might have a little bit of an issue is when we use something like sodium carbonate. Now, sodium carbonate is a very good primary standard. You can make a standard solution from sodium carbonate, but notice how its formula here says Na2CO3 .NH2O. That N could be 0, 1, or 10, and we have no way of working out what it is. So it's fine. We can use sodium carbonate. It ticks all the other boxes. Molecular weight of 105.988. It's quite high, low percentage error. It's a solid. It's non-reactive, and we can obtain it in high purity. We just need to put this in a desiccator. Okay, a desiccator looks like this. We dry it in the oven. We dry the water off, and we leave it in a desiccator. Usually it's got some silica gel or another type of desiccant in there. You've probably seen these around the labs. They look a little bit like this. Okay, and it makes sure that it absorbs any water that comes into contact with it, so it stays dry before you weigh it. So it has a really accurately known composition when you weigh it, unlike sodium hydroxide, which will react with water and carbon dioxide. So it's a bit of a no-no. Oxalic acid is a nice acid to use. Sodium carbonate is a nice base to use. Okay, these are two really good primary standards. Okay, so we can make a standard solution with a primary standard. It's not that you can't make a standard solution out of hydrochloric acid and sodium hydroxide, but we'd call them secondary standards because they'd need to be what we call standardized first. We'd need to actually measure them against something that's very accurately known. So just going back to here, properties of primary standard. This is in your exemplar document. It's solid, so it's easy to weigh. It has a high purity. Okay, can be obtained from a chemical supplier in high purity. It has a known composition formula, so none of this, we don't know how much water is in the crystal kind of situation. It has a high molar mass to reduce percentage error, and it should be stable. We can't have it reacting with atmospheric gases or water, otherwise we don't know our composition of what we're weighing, and we actually don't know, we can't then work out from this the number of moles, okay, whether it's 7 grams or 6 grams in the sample. It's going to be inaccurate there. So this is how you pick a primary standard.